Whoa, the wind outside is freezing. Glad I've got my hat. I wouldn't be so sure about that. Looks like you got zapped. Oh, yeah, it's my rock star look. Static electricity always makes my hair do this. Mine, too. What's going on? It's electricity. You know, the energy that's caused by moving electrons. Oh, electrons are connected to electricity. I guess that does make sense. And you know that electrons are part of every atom. Yeah, they're like little moons zipping around the nucleus. Electrons have a negative charge, right? Yep, the opposite of protons that have a positive charge. Pro for positive. That's easy to remember. Hey, do opposites really attract? In this case, definitely yes. The electrons and protons pull towards each other. And the neutrons? Don't have any charge. Not the life of the party, huh? Not neutrons, but electrons are definitely partiers. They jump at the chance to visit another atom. So sometimes when objects touch or rub together, electrons hop from atoms in one object to the atoms in the other. And when they do, they cause little bursts of electricity. Hey, was that why I heard your hair make crackling sounds when you took off your hat? Exactly. Electrons rubbed off my hat onto my hair and gave my hair a negative charge. Static electricity. It happens when you rub a balloon against your sweater, or your shoes rub on a carpet, too. So that's what made your hair stand up? Yep, since like charges repel, all the negatively charged hairs pushed away from each other and poof. What about lightning? Is it caused by static electricity, too? You bet. Clouds build up electrons and a negative charge until, zap, a giant burst of electricity flashes toward the ground. And static electricity is what makes socks stick together when you take them out of the dryer. I bet that means they have opposite charges, since opposites attract. Good thinking. When socks stick together, it's because one's got a positive charge and one's got a negative charge. Wow, electricity is amazing. And it's everywhere. It happens naturally in things like lightning, but we create it too. We build dams to turn water power into electricity. And wind turbines to turn wind energy into electricity. And even burn fuel to make energy from generators. And all that electricity lights our streets, houses and businesses, and stores. And runs machines everywhere. Incredible! All because tiny electrons move from atom to atom, giving off electricity. Who knew that just touching or rubbing things together could make electrons jump from one atom to another? Or that those electrons make negative charges build up and cause static electricity. Or that like charges repel and opposite charges attract. It's mind-blowing. Really, life without electricity would be positively primitive. Well, I could live without my static zapped hair, but I sure couldn't live without this. Electricity rocks. Play it, girl.
All right, eighth graders, we are going to go ahead and start our notes on electric charges and static electricity. So we are going to do our 7.3 notes. So just follow along with me and you're going to fill in your notes as I do on your screen. So by the end of this lesson, you should be able to explain how forces between objects act when the objects are in direct contact or when they are not touching. In this case, you're going to talk a lot about electrons. But first we need to talk about what is an electric charge. So let's start with that, okay? Matter can have a negative or have a positive or negative charge, or be neutral and have no charge. Atoms, which make up all matter, are composed of smaller particles called protons, which have a positive charge in the nucleus. Neutrons, which have a neutral particle in the nucleus. So right here in the middle of the atom, you will see these white dots. Those are the neutrons, and the red dots with the plus sign, those are the protons. And then on the outside of the nucleus, you'll have electrons, which have a negative charge on the outside of the nucleus. So here, these blue dots in the atom, those are called electrons. In your figure that you guys have on your paper, you can actually label these. I can't do this online because this is an actual static picture, but you can actually label on your notes that A is the nucleus and B is the electron. So go ahead and do that in your notes. Okay, atoms are neutral but can take on a charge by gaining or losing electrons and becoming an ion. If an atom loses electrons, that means loses one of these negative particles, okay, that new charge of that ion is now overall positive. And if an atom gains an electron, means adds on one of these negative charges, then the overall charge is negative. So now we're going to actually talk about the forces between particles. And then this is where we actually talk about positive and negative ions being attracted or repelled to each other. So you're going to look at this YouTube on Coulomb's law, watch it real quick, and then we'll go over the rest of our notes.
Now, matter can be electrically charged. Charges can be positive, negative, or neutral. If an object is neutral, it has zero electrical charge. Here's the representation we'll use for a positive charge, a negative charge, and a neutral charge. Coulomb's law says that like charges, that is, charges with the same sign, repel each other, while opposite charges attract. If we put two positive charges close together, they'll repel each other since they have the same sign. The same goes for two negative charges. If a positive and a negative charge are near each other, they'll attract. And neutral charges won't interact with electrically charged objects. Now, the closer two charges are, the stronger the force between them will be. So let's return to our positive and negative charges. When they're far apart, like we show them here, the force between them is relatively weak, as indicated by the short arrows. As we move the charges closer together, the forces get stronger, which we show by the arrows getting longer.
So let's summarize what we've just watched from Coulomb's law. So now you'll notice that the words are in blue, makes it a lot easier to see. So Coulomb's law, what affects the amount of force between particles? Well, there's two things, the charge, which means positive or negative, and the distance between them. Electric fields are what we consider non-contact forces, meaning the charged particles do not have to be touching in order to show a force in each other. Let's talk about the next thing, which is a charge. A charge can either pull particles together or push the particles apart. So again, charges are the positive and negative. So let's think. What kind of charge would be pulled by a positive charge? So in other words, what would attract a positive charge? Well, it would be its opposite, a negative charge. Its opposite. So what kind of charge would be pushed away or repelled by a positive charge? Well, another positive charge. So the same charge. So basically the statement goes along with saying that opposites do attract. And it goes along with the whole Valentine's Day theme, which is coming up. Okay, also the magnitude of the charge, which means, let's try in magnitude, mag. Of the charge, meaning how positive or how negative the charge is. So you can actually have different levels of how positive or negative a charge is. We'll talk about that. So this affects how the strength of the attraction and the repulsion. This means there would be more attraction when particles have a greater difference in charge. So in other words, would a positive 3 particle be more attracted to a positive 3 particle, a negative 1 particle, or a negative 3 particle? Okay, so let's think about this. Okay, first you would have a positive 3 particle and you want it to attract. So obviously the first step, it has to be negative. Okay, so that leaves us either negative 1 or negative 3. And the idea that the higher the magnitude, the more attractive it is. So the answer is, basically, your answer should be negative 3. Okay, and the reason is it has a stronger opposite force or magnitude. Okay. So let's continue going. So not only does magnitude affect the attraction or repulsion of particles, also distance between particles affects the amount of electric force between charged particles. The closer charged particles are, the greater the attraction or repulsion between the particles. So what happens to the amount of force as the particles move away from each other? So the attraction or repulsion is less. Okay. Is it true if you have a balloon in somebody's hair? Okay. So if we were actually doing this live, I would be able to show you that when you rub somebody's hair with a balloon, the closer you take that balloon toward the person's hair, the more attracted the hair is to the balloon. And then the further away you take the balloon from the person's hair, the less attractive that it is. Okay. So let me show you basically. Try to find a picture here. Okay. Actually, let me show you with a diagram. Okay, so here I've got a balloon, okay, and it's got positive and negative charges to it, okay? So what I'm going to do is I'm going to rub this balloon against the sweater. And what I'm going to do is by doing that, I am going to charge the balloon because right now it has equal number of positive and negative charges to it. So it's neutral. But when I rub the sweater against the balloon, it's actually going to take away all of the negative charges from the sweater, okay? Now, when I put it against this wall over here, notice what happens to the electrons. So it's going to make the electrons repel because they're opposite charges. And it's going to, as I move further away, the attraction is not as strong. But when I get closer, the attraction of the repulsion is stronger. Away, not as strong. Toward, stronger. There's definitely a stronger attraction. Okay, so let's reset here and we'll put two balloons. So now I'm going to do the same thing here. Okay. Watch what happens here. Didn't do what I wanted to do, but basically you get the idea. Closer, repel, more, farther away, less repulsion. Okay? Oh, and look what happens when I let go of the balloon. Boop. It's attracted to the sweater because opposites attract. So when I let go of the sweater here, boop. When I let it go over here, it's not attracted to the sweater as much because it's too far away. But when I get closer, eventually get to a point where it will have an attraction toward it. Notice that it doesn't attract to this balloon here because it's neutral. It's not, doesn't have a more positive or negative charge. That's why I wanted two balloons. Okay, so it's not going to be attracted to that balloon. Okay, but if I reset it to be like this, and I take some of this, oop, it'll actually repel off the other balloon and towards the sweater because this is now more negative. Okay. All right. So is this true if you have a balloon in somebody's hair? The answer is yes. Okay. As you saw, there's different ways that a particle can become charged. The one I just showed you in that particular demonstration is something called friction. Okay, it's the rubbing of two objects together can cause electrons to flow from the object with low affinity, meaning I don't like electrons, the object with high affinity, meaning I love electrons enough to steal someone else's. So again, biggest example for this one is rubbing a balloon on a sweater. Okay, the sweater has a low affinity for electrons, and the balloon has a high affinity for electrons. Therefore, the electrons go to the balloon. The second way a particle can become charged is something called by contact. Okay, if a neutral object touches a charged object, some of the charges will move between the objects. Okay, greatest example of this is when you actually like touch a doorknob after it has been charged. You get that shock, okay? But you have to actually touch the doorknob in order to become charged. That's basically what's happening is the electrons are traveling from the doorknob to your hand because your hand is neutral, so it's going from one object that is charged to your hand that is not charged. Another one would be when you actually take your plug and put it into an outlet, okay? Your plug by itself is neutral, but once you put it into the outlet, that outlet is charged, so the electrons are going to travel from the outlet to the plug. Obviously, that's the biggest reason why you don't stick your finger into a socket or you don't stick a pair of scissors into a socket. Okay, and then the third way that items can be charged is something called induction. And this is charged when an object is near but not touching another object. The electrons in the neutral object can be realigned. This happens when a negatively charged object comes near a neutral object and forces the electrons in the neutral object to the other side. The charged object stays charged. The neutral object stays neutral, which means they have an equal number of positive and negative charges, but will be polarized. A good example of induction is with lightning during a storm. So when charges eventually move from one object to another, that is called electrical discharge. Okay, so here is what we call induction. Okay, so in other words, what's happening is in a cloud, the positive and negative charges separate from each other. So here you can see in a cloud, the positive are at the top and the negative are at the bottom. Okay, so they basically separate. And then so what happens is the Earth is naturally positively charged. So what happens is the negative charges from the cloud travel down and meet up with the positive charges of the Earth and basically eventually meet, and then you get what they call the electric discharge. Okay, so watch this video clip of how lightning is made, and we'll go right back to this.
You're a big fan of thunderstorms.
I am. I love thunderstorms as long as they're not accompanied by tornadoes.
Oh.
Which in Wisconsin happened a lot. But around here, I remember we seemed to have a lot more back in like the 90s.
Yeah, we're talking about severe weather. We did seem to have a lot more thunderstorms back in the 90s, and we really haven't had nearly as many over the past 10 years, at least, if not longer than that. We get the storms, but not like it was. That was an abnormally large amount of thunderstorms. We are talking thunderstorms and lightning. Got 3 questions from Monroe Elementary.
Hi, my name is Jeremiah. Hi, my name is Ruben. We go to Monroe Elementary. And our weather question is, what is lightning made of?
Hi, my name is Amy from Monroe Elementary. My weather question is, why does clouds rubbing together make lightning?
Hi, my name is Cassandra. I go to Monroe Elementary. And my weather question is, what causes thunder to have sound?
All right, lightning and thunder questions from 4 students from Monroe Elementary. So we're going to try to cover it all right here. First of all, how does lightning form? Well, it's electricity is what we're talking about. And the atmosphere is actually rubbing against the ground, creating static electricity. And so the bottoms of the clouds, you'll have negative charges here. There might be positive charges at the top of the cloud. So you get lightning from positive to negative inside the cloud. But that charge differential, we have positive charges near the ground. They start to line up, and they'll even start to run right up the trees here. And if you're in the area, if you get that feeling that your hair is starting to stand on end, that's the positive charge is actually running right up you, and lightning is looking for a spot to strike. And so that's when we get the electrical discharge here, the lightning striking. And then we have now a redistribution of the charges here, pluses and minuses, until it builds back up again. So there's a thunderstorm danger. When you see a thunderstorm off in the distance, you have to keep in mind that lightning may extend out 4 miles. When you hear the phrase out of the blue, it comes from the phrase bolt from the blue, or a lightning bolt that comes out of a blue sky, because it may be blue skies here, but that lightning bolt can shoot out 4 miles ahead. So near thunderstorms, you want to stay away. And if you want to check the distance of the lightning, time lapse, or I should say the time lapsing between the lightning and the thunder, if it's 5 seconds, that's 1 mile. And so anytime the sound is 10 seconds between the flash and the thunder, you want to take shelter. In other words, just a couple of miles away, take shelter, because again, that storm could be affecting you. How do thunderstorms occur, or how does the thunder occur from the lightning? It's actually a rapid expansion of the air. We're heating the air to 30,000 degrees in an instant. And so the heat expands the air very, very quickly, and then the lightning bolt is gone like that. The air cools and it comes back together, and that's the path of the thunder, making those compression sound waves come towards you. That's where the thunder comes from. They both happen at the same time, but lightning travels a lot faster than the sound does. Lightning hits the earth 8.6 million times each day, so the atmosphere is constantly trying to balance out the charges, and we get lots of casualties from lightning, so we have to beware of lightning here.
Hopefully that video clip helped you realize how dangerous, but at the same time, how fascinating lightning is. Who realized that how many times lightning actually strikes our planet? There actually was a great video that NASA actually recorded of the Earth, and astronauts could actually see lightning bolts from space hitting the Earth. It looked like basically a fireworks show happening on Earth. This also goes to the fact of why you should never stand in the middle of a field by when you're all by yourself when during a lightning storm, because basically what ends up happening is you turn into a lightning rod. The protons travel all the way up your body, and at the very tip of your head, you're basically a very large proton. And so when the clouds separate their electrons, they're going to find the tallest thing that has a proton to it, and that would be you. So again, also standing underneath a tree would not help, because then you are next to the tallest thing that has positive charges on it, and so the lightning is going to, or the electrons are going to find that positive charge and strike it. So again, big reasons why you should never be outside during a lightning storm. Lots of houses and buildings now have what they call lightning rods, so that they can then take the current, those electrons that are coming from the sky, and actually safely travel it down the rod into wires and put it back into the ground. That's what's called grounding the wire, or grounding electricity. Okay. Houses also have grounding wires too, to direct all extra electrons to the ground so that nobody gets shocked when you plug something in. So let's finish up this last part of our notes, okay? And this is, how does the material type affect the flow of charge? So just actually talking about it, you may have remembered some of this from last year if you had me as a 7th grade teacher talking about circuits and everything. So we have something called insulators that will not let electron flow easily. Many insulators are used to keep conductors safe. Insulators would be like plastic, especially like the plastic around wires. Rubber is a great insulator. Sometimes glass can be an insulator. It's not a very good insulator, but it's sometimes used. That's why some thermoses will have actually glass on the inside. But the best one obviously is plastic and any rubber type material. Opposite of insulators are conductors. This will let electrons flow freely. This is why it's good to have copper electric cord surrounded by a plastic or rubber cord. Copper is the best conductor in the world. That is why copper is used in a lot of our electrical devices. It actually is great for letting electrons flow through, and then it doesn't overheat. Then you have something called a semiconductor, which are materials that control the flow of electrons. Okay, they're not great conductors, not great insulators, they're kind of in between. Remember that like energy and matter and mass, electric charge is conserved. It means electrons are never lost. They're just transferred from one object to the next. So think of it this way: when lightning strikes the ground, those electrons are now in the ground, and those electrons will then travel onto something else. Or if you think about it this way, when you have your Chromebook and you plug it into the outlet, there's electric charges that go from the outlet into your cord, and from your cord into your Chromebook, and from the Chromebook it lights up your Chromebook, and those electric charges are then transferred into light energy, and so you can see your Chromebook light up, and so on. So again, electric charges are never actually lost, they are just conserved. So this is it for your electricity notes. The next set of notes we're going to go through are magnets and electromagnets. So play the next video if you want to move on to magnets and magnetism.